Integration by parts. Integration by parts is not required for AP. I do it at this time for a couple of reasons. One, I like it. And I'm going to teach something that I like within the subject matter. Two, this is the perfect time to introduce it to you. It fits in with what we're doing at this time. Okay. Three, you will see this again when you take calculus in college, and I want you to be exposed to this now before you are then when you have to have it. So it's something that can be difficult. I know that some people struggle with it, in college in particular. I like to do it now because I can kind of be a little more relaxed than most of your professors are going to be in college about setting this up and doing it. Okay, I was fortunate. The professor I had that covered this actually had a computer program. We'd spend a day in the computer lab just picking our U's and V's without actually doing any integration. Okay, I don't think that happens very much at all. In fact, I know it doesn't happen very much at all. Yeah, I can't even do it here because I don't have the software to do it. Okay. But it's one of those things that can be difficult to wrap your head around. It's not that bad. I do a soft sell on it. We don't do a lot. The homework problems, yes, they're not going to be the easiest in the world, but they won't be that bad either. You will have a couple of questions on the chapter test where you have to do a UV substitution, integration by parts, but you will not see it again in this class after this test. You will have to do U-subs, but you won't have to do what we're doing today after the test at the end of this chapter. No, not on the final, not again after this chapter test. Okay, I do it now because it fits in really good with where we're at. And I think it's a good thing to see it now before you have to see it in the class in college where you're going to have at minimum twice as many students in the class as you have in here. Minimum. Even if you go to a small school. And you go to a bigger school, you might have a couple hundred taking first and second and third semester calculus. Okay, it's tougher to do when you're in that situation. You don't get the time to ask the questions and things like you can in here. Okay, so it's a lot harder. That's one of the advantages of taking AP calculus in high school. Is they're in a very small classroom. It's a lot easier to ask questions, work with a professor, so to speak. You know, you go to a bigger school like UC Santa Cruz, you can have a couple hundred kids in your first semester calculus class, and you never actually talk to the professor, you talk to the TA. Okay? So, do not worry about getting these next parts down in your notes. This first page is basically to show you where the formula comes from. And I think it's a nice one to see where the formula comes from. So, if U and V are functions of X, just like F and G, only we're using U and V. It's called UV substitution, integration by parts, UV substitution. I'm going to do a lot of writing using different colors today. Okay, it's the best way to keep things organized. So, product rule. The derivative of one function times another, the derivative of UV, is U derivative of V plus V derivative of U. That's the product rule, right? So if I take that product rule and I integrate both sides, like I said, you don't need to get this written down, don't stress writing it down, but I integrate both sides. Okay? So I take the integral of the derivative of UV, the integral of U dV, and the integral of V du. They're all functions of X, so this integration with respect to X. Okay. The integral of UV dx, this just the integral of the derivative is just that. Okay. The integral of U V is V du. Okay. And the same thing here. I get the same thing doing the derivatives. I get the functions and then the integral of that. If I rearrange this, I get the integral, and I just move things around. I get the integral of U dV equals UV minus V du. Okay. This formula, this is our formula we're going to use. comes from the product rule. And I just wanted to show you where the formula you're using comes from. Okay. This is what you have to have down. Okay. The integral of u dv equals uv minus the integral of v du. U and v are functions of x, or functions of whatever variable we're dealing with. Okay. The idea is you take a complex integral, something extremely complex, and you make it into a partial solution, the uv, and a simpler integral. Okay, that's the idea behind this. You're taking something that's really complex, that's very difficult to do, and transforming it into a partial solution and a much easier integral to solve. So you will have to do another step of solving the second integral here. Okay? But that's the idea behind integration by parts. Take something nasty, get a partial solution and an easier problem. That's what U substitution is. U substitution, when we're doing that, take something nasty, make it into something easy. Same idea here. Only it's something even nastier, so I can't come up with the full answer on one step. Okay. Here's one of the couple of keys you need to have in there. Everything, absolutely everything in your original problem will be replaced. Everything in the original, or I should say everything in the original problem will either be u or dv. Your original integral will be either u or dv. You're going to take everything that's there. There will be nothing left over when we split it into parts. Okay? Absolutely everything. This is one of the keys. Nothing, not even a constant, is left behind. Everything is broken into those two parts. Okay? Everything. And that's the decision we have to make. And here's the other thing. You absolutely have to be meticulous in your work. You cannot be sloppy. You cannot be careless. There's too much going on. It is way too easy to get lost. You absolutely need to be meticulous. You need to state and show every silly little thing, because you can get lost like that. When you get lost, you're screwed. Okay? You absolutely must be meticulous in your work. Absolutely. Okay? Now, hardest part about U substitution, deciding what U is. Hardest part about UV substitution is picking your U again. However, we have a rule to help us decide what our U should be. Lipit. Okay. Lipit is what you use to pick your U. If you have a logarithm, U will be your logarithm. If you do not have a logarithm, then you look to see, do I have an inverse trig function? If I have an inverse trig function but no logarithms, I let U be my inverse trig function. If you do not have a log or an inverse trig function, then it is the polynomial. If you do not have any of those, then you let it be the exponential function. If you do not have any of those, then it is a trig function. If you do not have any of those five things, then what are you doing UV substitutions for? Okay? Because you don't need to. And once again, I want to stress, I said this several times already in this chapter, the methods are not interchangeable. Something that you do a U substitution on, a UV substitution will not work, and vice versa. When you are doing an integral on test, on a review, first, can I just do an antiderivative? If I can just do an antiderivative, please use the antiderivative. If that doesn't work, then you look at it and say, Well, can I do a U substitution? If that doesn't work, then you hit the UV sub. This is the last thing you try, not the first thing you try. Because if you do this on something that does not work, for UV sub, you will make your life miserable because it will get harder, not easier, and not be solvable. You cannot use UV sub to solve something that doesn't need a UV sub. It will not work. Okay? Yeah, and the reason we're doing this is hopefully eliminate the U. Because what you're going to do is you're going to take the derivative of whatever your U is. And if I have a logarithm, what happens when you take the derivative of a function of a logarithm? The logarithm goes away. Take the derivative of an inverse trig function. Your inverse trig function goes away. You get something else that's not pretty, but it's gone. That's the idea, to make it simpler. If I take the polynomial may not go away, but it becomes a simpler polynomial with each derivative. That's the idea that we're trying to do. Okay, so here we go. We're doing the integral of x cosine x dx. Okay, choose your u and your dv carefully. If you do not choose your u and your dv carefully, it will work. And if it doesn't work, if you end up with something that's not simpler, swap them. Try again. So if I go back to Lipit, first thing in Lipit, logarithms. Do I have any logarithms? No, so I don't have to worry about that. Next thing, inverse trig functions. Do I have an inverse trig function? No, that's just regular trig function, not an inverse function. Next thing on the list is a polynomial. Do I have any polynomials? Yes! What do you think x is? X is a polynomial. Let u equal your polynomial. So u is going to be equal to what? X. U is equal to x. And everything needs to be either u or dv. So I use x is my u. What's my dv? Cosine x dx. Everything. Everything is one or the other. Everything that's in the integral is in one of those two places. Everything. You don't put everything in, you're not doing it right. Okay. Now, I have u. Now I need to do my next step so I can do my u integration by part substitution. So u is equal to x. If I have u, then I need to find du. This works just like what we've been doing. Take the derivative. The derivative of u is du. The derivative of x is dx. 1 dx. Okay. If I'm starting with dv and going to v, what am I doing here? I'm doing the antiderivative. I'm integrating it. So that means I take the antiderivative of the cosine of x. What's the antiderivative of the cosine?
Negative sine.
Just sine. That's an easy one to get messed up on, believe me. Sine of x. Now, I need to pause a minute and go back, because if I don't have this written down in front of me while I'm doing this. Okay. Integral of u dv is equal to uv minus the integral of v du. I still got to stop every once in a while because it's not fresh in my mind. Okay, so I have all my parts. I have my integral of u dv because that's what I decided. I know what uv is because I got u and v, and I know what v du is because I've got v and du. I take them and plug them into the formula. So my integral of u dv is equal to uv x sine x minus the integral of v du. v du. Now, I love having colors because it makes it easier to see where the u's and v's and db's and all that stuff comes from. It lines it up good. But do you see what we just did here? We took something pretty complicated that you just can't do the way it stands. Have a partial answer and a very simple integral to do. Something really nasty into something partially done and really easy. That's the idea behind a UV substitution. I'm not done. I still have to do this second integral, but hey, that's easy. I can do this, no problem. That's not a big deal. Okay. So my final answer, the next thing I'm dealing with, is I get x sine x, and then I do the antiderivative of the sine of x. What's the antiderivative of sine x? Negative cosine x, but I already have a negative here, so it ends up being plus cosine x. And then what do I have to have because I don't have bounds? Plus c. If you do have bounds, ignore them till you're done and then plug them into your final solution. Okay? If I have bounds on the original problem, I ignore them until I get to here. Don't worry about the c and evaluate after I've done all the antiderivatives and all that stuff. Ignore them until you're done and then plug them in. Trust me, it's not worth trying to do it partially as you're working along the way. It'll make things even worse and more confusing. Okay? If you remember the formula and you remember Lipit, it's not that bad. But you have to be meticulous. You absolutely have to be meticulous in your work or it doesn't work. Yes, sir.
So if you had bounds, plug them in here.
I'd plug them in here. If I had bounds, I would wait till here and then plug them in at this point. I would not touch the bounds until I got to this answer here and then plug them in. It's not worth it. It's not worth trying to do as you're working through the problem. Just ignore them till the end. Trust me. Okay. I know what I'm talking about. Okay. How are we doing so far? Thoroughly confused? Slightly confused? Okay. Clear as mud? Okay, example number 2. We have to decide our U and our dV. That's your first step. Once again, flip it. Okay. Do we have a logarithm? Yes, we have a logarithm. Oh my God, I love it. What is our U then? Natural log of t. What's our dV? Everything else. T squared dt. Everything else. And it doesn't have to be in the order like it was. You know, the first example, the U was first, and then the dV was everything that followed. It doesn't have to be that way. It can be whatever order it is. Okay? But that's what you do. So, since I already have my red pen in my hand to match up with the dV, let's do the antiderivative. Antiderivative of t squared. 1/3 t cubed or t cubed over 3. Either one would work. Now I'm going to pick up my blue pen so we can do the derivative of the natural log of t. What is the derivative of the natural log of t? 1/t dt. Do not forget your dt's. Do not forget your dt's. And now here we go. The integral of u dv, which should be, let's see, t squared dt, and I'm just doing this so we can help keep track of things, ln of t equals uv negative 1/3 t cubed natural log of t. I'm just writing it so it looks pretty. I don't want to put the natural log of t 1/3 t cubed because then might think you're taking the natural log of everything, right? Okay. And sorry, my LNs look like crap. Minus the integral of v du. I'm going to write it out as it is. 1/3 t cubed times 1/t dt. Look at what happens. I want to simplify before I get a little carried away. So this equals 1/3 t cubed natural log of t minus the integral of 1/3 t squared dt. T squared, because it's t cubed times 1/t. What's t cubed times 1/t? T squared. Right? And we can do the antiderivative of 1/3 t squared. So I end up with 1/3 t cubed natural log of t minus the antiderivative of t squared is 1/3 t cubed times the 1/3 that's already there, right? The antiderivative of the t squared is 1/3 t cubed times the 1/3 that's already there. So I have 1/9 t cubed plus c. Can't forget the ocean. That big blue wet thing.
A little salt.
Not as salty as my wife's dinner the other day. My wife, her idea of salting food is to wave the salt shaker over it. Not I'll tell you, just to kind of pass it over it. That's her idea of salting food. She salted the other day, and it was so bad. And she's like, "Oh my God, I'm so sorry, I oversalted." I'm like, "Oh no, it'll be all right," because you undersalt so bad. Oh my God, it was inedible. It was that much salt. We got a good laugh. Enchiladas. She made the sauce from scratch and just totally oversalted. And she doesn't do that. She doesn't. She doesn't do that normally. This is like, but it was horrible. We ended up throwing it out. I hate wasting food. She does too, but it was inedible. I mean, you take a couple bites and you're feeling sick. There's that much salt. Yeah. Okay, questions? It's not bad, is it? Yeah. Okay, now we're going to step it up a little bit, and we're going to introduce something new. Okay. No, this is the part you're going to hate. Trust me. This is not the part you're going to hate.
Are you sure?
Yes, what's the question? Yeah. Okay. Anybody here ever see the movie Stand and Deliver?
Well, we watched the Spanish one this year.
You did?
Yeah.
Oh, cool. So he actually does this in the movie. Stand and Deliver is an interesting movie. It's about Jaime Escalante, who stepped into the worst performing school in Los Angeles, Garfield High School, and basically created a calculus course. And the kid, yeah, you've seen it probably. Okay, there's a scene where he does this, where he's showing, oh, and he's chewing out the kid's thoughts. You gotta do the tic-tac-toe. That's what tabular integration is. That scene where he's like yelling at the kids, because he yells at the kids all the time. So tabular integration is, instead of doing a UV substitution, it is UV, but it's a way of doing UV in a slightly different circumstance. What you're going to do is, rather than U and dV, we're going to break it up into break the integral into two functions, f of x and g of x. F of x is when one of the functions is a polynomial that will eventually reduce to 0. Now, if I have a polynomial, and we did on the first problem, right? That polynomial reduced down in one step because it was only to the first power. If you have a polynomial to a higher power, you're going to have to do repeated integration by parts. Let's say on that first problem, instead of x, cosine x, we had like x to the 5th cosine x. Well, then you're going to have x to the 4th. And then you're going to have to do it again because you're going to have x to the 4th, and you're going to have x to the 5th, blah, 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 integral x to the 4th sine x. And then you're going to have to do UV on that integral. And then you're going to have to do it again. And you're going to have to do it again because the polynomial, you're going to have to do a UV substitution every time until the polynomial finally goes away. Tabular integration is a way of doing UV substitutions if you have a polynomial to a higher power that is going to take a little while to go away. It's just a version of UV substitution. You're still going to be doing derivatives and antiderivatives. Okay? So what you do is you break it up, you set up a table, and do repeated derivatives until the derivative of the polynomial becomes 0. You do corresponding antiderivatives of the other term, the other function, because it doesn't go away at all. Until, like I said, you do it until it fills in, and then you can get your answer from that table, and I'll show you how to get the answer from the table. Okay. You ready to go on to the next page yet or not? I'll give you guys a second. All right. Okay, so tabular integration. Use alternating signs. So this is what we're going to do is, rather than picking a u and a b, we're picking out an f of x and a g of x. Okay, so we have to decide what our two functions are. The f is easy. The f is what our polynomial is, x cubed. The g is everything else. Okay, e to the negative 3x. Don't worry about the dx in your f and g when you're doing tabular integration. It's just the function part. It's just the function part. Okay, so, and I'm going to scroll to get the table up a little higher. Let's do this. So, f and its derivative. So we start with f, and what color was f? F was red, just to keep the colors going. So, x cubed, right? X cubed. And then we take derivatives until it goes away. So we get 0 in this column. Just repeatedly take derivatives. F and its derivatives. So that means we get 3x squared. Derivative of 3x squared, 6x. Derivative of 6x is 6. Derivative of 6 is 0. Now we're done. How many of these you have depends upon the power. You start with the highest power of your polynomial. Okay. If I have it to the 5th or 6th power, I got another couple of layers going on here before I'm done. The other column, I take g of x, e to the negative 3x, e to the negative 3x, and I do antiderivatives of that. I integrate it until this line, until I get down to the same number of lines. Okay, because it won't go away. Because the antiderivative of e to the x is never going to go away. So what I have to do is I just keep doing it until I match the two columns. So the integral of e to the negative 3x, negative 1/3 e to the negative 3x. And the pattern here, the signs will change. Yes?
Why is it not to the negative 2?
Because you don't take the derivative of the exponent. Well, you do, but that's you don't reduce the power. I'm not reducing the power, right? Exponentials, you don't reduce the power. Only reduce power on polynomial. Variable, don't reduce powers on the variable if it's in the exponent. Okay, why do I have the 1/3 on there? When I take the derivative of this, it's e to the negative 3x times the derivative of negative 3x, which is negative 3. Do I have a negative 3x? No. So I need a negative 1/3 to cancel the negative 3. Right? Antiderivatives. So when I take the antiderivative of this, it's really nice is one, the sign is going to switch, Sign will switch back and forth. And I'm going to have 1/9 out in front. Positive 1/9 e to the negative 3x. The antiderivative of that, negative 1/27 e to the negative 3x. And the antiderivative of that will be 1/81 e to the negative 3x. If you don't believe me, take the derivatives and work your way up and see if you match. Remember, when you're doing antiderivatives, you have to account for the constants. You have to account for those kinds of things. Okay. I got the table filled. Now I need to take that table and write my answer. Here's what you do. You work diagonally. My first term is going to be made up of these two terms times each other. My next term is these two times each other, but it's opposite. My next term is these two times each other. And my last term is these two times each other, and it's opposite. So I go plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, multiplying the diagonals to get each term for my final answer. Okay. So the integral of the integral of x cubed e to the negative 3x dx is x cubed times negative 1/3 e to the negative 3x, which will give me negative 1/3 x cubed e to the negative 3x, minus whatever these two are multiplied together, minus, and because they're both positive, it's fine, 3x squared times 1/9 e to the negative 3x. 3x squared, 3 times 1/9, that gives me 1/3 again. X squared e to the negative 3x. Plus 6x times negative 1/27 e to the negative 3x. 6 over 1/27 reduces to 2/9. Minus 2/9 x e to the negative 3x. And then 6. And then it's minus 6 times 1/81 e to the negative 3x. 6 over 181 reduces to 2/27 minus 2/27 e to the negative 3x. Let's see. That's my answer. Okay. Now, what I have done here is I have done repeated integration by parts in one step. Technically speaking, this is integration by parts. This is my u dv. This is my uv. And then from here on out, I would have an integral for my v du. Take the derivative, do that one again, and then I get this plus another integral. And I get this plus another integral, and so on. Rather than doing integration by parts over and over and over and over again, coming up with a uv and another 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 uv. That does the same thing. It only works when your u is a polynomial. The thing you are going to choose as your u is a polynomial. This is the only time you use this, because this is technically UV substitution. But instead of having to do UV sub, and then another UV sub, and then another UV sub, that's what that does for us. U du, dv v, dvv, dvv, dvv. So we're doing the antiderivative each time. We're doing the derivative each time. This would be the this would be the u dv choice for the second integral. This would be the u dv choice for the third integral. This would be the u dv choice for the next integral. That's what this is. It only works if you have a polynomial. Would I do it if I have a polynomial third or higher? Yeah. Second, maybe. If I have it, my polynomial is to the first power. Oh no, I'm not doing that. Not going to happen. It's too much work for just one. Okay. So it depends upon a polynomial. If you have a polynomial second degree or higher, do it. If you have a polynomial first or 0 degree, because there is such a thing as a 0 degree polynomial, that would be a constant. Okay. Don't use that for this. This for that. But wait. Okay. Everybody listen up. UV substitution. Let's pick our U and our V. Okay. Go over here to the side. U equals dV equals. Do we have a logarithm? Is there a logarithm in there? No. Come on. Do you see an L followed by an N or an L followed by an O and a T? No, we don't have a logarithm. Come on. You guys should be able to recognize logarithms. State with confidence that there is no logarithm. Is there a logarithm in that integral? No. Thank you. Is there an inverse trig function? No, you did not see a -1 on the trig. Right? No inverse trig. Is there a polynomial? No, you don't see a polynomial either. So let's see. Lipid, logarithm, inverse trig, polynomial, followed by
Exponent.
exponential. Do we have an exponential?
Yes.
All right, those of you that said no, shame on you. E to the x, remember the exponential, so the exponent is in there. So that means our u is e to the x. Okay. Do I have a polynomial? Do I have a polynomial? No. So can I do tabular integration? No. Yeah. We don't always do what we just did. This is not Algebra 1 where everything is the same as the last thing you just did. Okay. So if u is e to the x, our dv would be cosine x dx. Thank you. I'll put a little tab on the end so it's not a V. Okay, does this have a little leg on it? No, it doesn't have a little leg on it. U's got legs. V's don't got legs. All right then. Okay. So if u is e to the x, what's du? Okay. Okay. Du is e to the x dx. V would be sine x. Okay. Now we do our substitution. You do want to rewrite the problem down. E to the x cosine x dx equals uv e to the x sine x minus integral of v du. E to the x sine x dx. Oh crap. Doesn't look, does that look any better? What's the difference between what I started with and what I have now?
It's more complicated.
It's a little longer. But let's soldier on. And do it again.
Let's go.
Okay, if you quit now, you're quitting while you're behind. And we're not quitters in here. So, for this equation here, u
Oh, I see.
dv. What's my u in the second integral? E to the x. So what's my dv? Sine x dx. What is my du? If u is e to the x, du is e to the x dx. And what's my v? Negative cosine x. All right.
Oh gosh, it's gonna be huge.
Trust me. I know you don't want to trust me. Trust me. Okay. Shh. Integral e to the x cosine x dx equals, shh, quiet, e to the x sine x minus the uv, my second uv, negative e to the x cosine x, because e to the x cosine x, right? Negative. Minus the integral of v du, negative e to the x cosine x dx. Okay, stop, chill. Okay, why is it negative? Because what's our v? Negative cosine. Watch your negatives and positives. Now, here we go. I want to get rid of the parentheses. E to the x cosine x dx equals e to the x sine x. Take this negative, distribute. Now, these two negatives become a positive here. This negative distributes, becomes a positive, and that becomes a negative there. I have two negatives, and then I have three negatives, right? Okay. Plus e to the x cosine x minus the integral e to the x cosine x dx. Okay, now, my answer is not complete because, okay, now, do I have an integral equal to non-integral? No, I have an integral equal to stuff and an integral.
Okay.
Yeah.
I cannot have an integral as part of my final answer. And you look at that and go, and how many of you are going, oh crap, I have to do it again. But wait, that is exactly what we started with, is it not?
Yes. Infinitely many solutions.
So this is not the integral that never ends.
There's an end.
We have one step to finish it.
Say screw it. No solution.
Okay. Shh. Quiet. Don't hate me. But you're going to like this one.
What?
Actually, I lied. We have two steps. No. Integral of e to the x cosine dx plus integral of e to the x cosine x means that I have two integral e to the x cosine x dx equals e to the x sine x plus e to the x cosine x plus c. But, is this what I started with? Not exactly, because I got two of them. What do I do to get rid of the two in the front? Divide both sides by 2.
And is that all right?
Well, I know this one is not like this.
And if you whine too much, this will be a test question.
Wait, really? So is that's
I said it's eligible. We did it. We talked about it. You're going to see it on your homework.
What is
I don't think it's probably not fair. I mean, I just.
No, it really isn't that bad once you get to this point, but it looks nasty. It looks like, oh crap, it's not going away. Mr. Norris, you said it would go away eventually. No, eventually it won't go away. But what you do is you get the same thing you started with, you just add it.
Yeah.
Now, be grateful. I simplified the problem because I've seen this where it's like cosine 2x and e to the 5x, and you end up with a buttload of fractions involved, and then instead of just adding the same thing to both sides, you got to add a fraction there. And, oh, it's just nasty. So I tried to make it easy that way.
Thank you.
Yes, this is an easy version of this problem. Okay. So, to kind of tie things up, this is all the versions of integration by parts that I showed you here. The first two are your basic ones. Pick your U, pick your TV, go from there, follow Lipit to get your U and V. Tabular integration is, once again, integration by parts, where your U is a polynomial that repeats, and the tab just lets you keep it organized so you're not doing this like we just got done again and again and again and again until the polynomial goes away. Because that's what tabular integration is. It's this with taking another antiderivative, another one, until the polynomial goes away. Tabular integration lets you shortcut repeated integration by parts. That's what that is. The other possibility is what we did here, where you get back as part of your answer what we started with. And then you just, oh, I put it to the other side, combine them up, and I go from there. Because eventually that will happen in certain circumstances, particularly where you have an exponential and a trig function at the same time. Okay. Generally speaking, your UV subs, when I give them to you, it's going to be one of the first three or your first choices. I'm not going to stick you with anything nasty. You might have a couple on your homework like this. You can have a couple on your homework like the tabulars. Most of them are going to be like the first two. On your test, I'm not going to nail you with anything that is horribly difficult to do, going to take you forever to do. So I'm not going to do that to you. But I do want you to see this. I do want you to know how to do this. Okay? Now,